Good morning, everybody. I hope that you are covered. And okay, so first of all, let me address the question from yesterday that I misunderstood the question. So the actual question is, how can one, in using light cone spinors, basically reproduce the correct relation for the time reversal action on the spinor side? So basically, one has in mind this kind of relation. That this is, by the way, the book by Itkinson and Zuber for quantum field theory. It's kind of, I think, one of the best books that there is. So this is chapter 3, section I do not remember. So you should be able to see the equation number. So please, if you want to check it in details, go here. So you get the transformation at the level of the spinor in position space, which acts as it should, with this A to be determined. That turns out to be this I gamma 1 gamma 3 or minus I gamma 5 times this C matrix, whatever. The problem is that, okay, in usual quantization, you have the action of this time reversal operator that acts on the creation of on the creator operator in momentum space in some way, where epsilon here is the helicity. And kind of in usual quantization is everything fine and dandy, because you get a relation between UK and UK tilde, where UK tilde, well, the tilde is mean that you reverse the spatial component of the momentum. But since in usual quantization this depends only on the 3 momentum, you actually get this basically the same spinor, but with some sign changes and whatever. And you can basically you are able to deduce this matrix A, imposing this equality. However, if you go to light front, as I more or less said yesterday, this tilde operation interchange plus and minus. So you get, instead of mapping the theory onto itself, you map in the theory of quantizing along the plus direction, you quantize along the minus direction. So you get the relation between the 2 quantization procedures. And if you want to derive this matrix A, the problem is that you have to take one of the 2 theories. So let's say that on the right hand side, since it has K tilde, so the spinor is written as K minus, you have to transform it back into K plus. So you have to actually revert. This is not put any particular kind of format, but this is Lorentz invariant measure. But the Lorentz invariant measure, you know that it can be written as I wrote it, so with the delta, the on-shell delta already taken care of. But you can also write it with the explicit on-shell delta that looks like something like this. So your Lorentz invariant measure, you can write it as the 4k delta of chi square minus m square, and then you have the theta. In this case, is theta of k plus, but okay, it is, this theta of k plus is the same as theta of k minus, depending on what you get out of this, because here you get k plus k minus m square minus kt square, where so you have 2k plus k minus, which is equal to something that is for sure not even equal, for sure greater than 0. And therefore, if k plus is greater than 0, so it is k minus, and vice versa. So theta of k plus k minus is the same, but you have to kind of unwind this this delta in the other direction if you're using time reversal. So one should first of all do that, and second of all, the problem is that the spinors that I gave you is they're written just as with plus components. One has to kind of work backward to understand how the minus component enters in the spinors. But that's I didn't have too much time to actually put effort to doing that. So I refer you to 2 papers, and then you can try to work out the details by yourself. I'm sorry about that. The first one is this PRD which is by Brodsky and Lepage. So here, I will probably send a reference later. So, but this is kind of also has been cited by Barbara Pasquini. This very famous paper on this topic. If you go to the appendix A, they gave you how they constructed the spinors, so the actual kind of way to parameterize this. You see that here there is no minus component, so you have to go backward, just kind of understanding what the minus component is. And by the way, the good component is when you quantize along the plus direction, defined as IF defined it. If you quantize along the minus direction, the plus and minus components are kind of interchanged. So you do not have to look at the plus component, but you have to look at the minus component to be the good component when you quantize along the minus direction. It's not really kind of mysterious. Just if you quantize along the plus direction, the plus component is the good one. If you quantize along the minus direction, the good component is the minus one. So there is really nothing there, but you have to do a fair bit of algebra to get it. Moreover, time reversal is not, for these reasons, is not kind of the most beautiful way to look at your theory when you quantize along the light front. And this is discussed in kind of, I think, very clear form in the appendix B of the Soper paper, which I refer to, which is kind of this infinite momentum helicity states by Soper, 72. So, and the main point is that we keep calling the light front helicity because in the infinite momentum frame, which is the natural way of looking at light front quantization, it's technical, but this light front helicity lambda here reduces to standard helicity. However, if you go and look into the definition of this light front helicity lambda, somewhere in the paper, I do not remember where. And here you see that, okay, he discussed this relation with ordinary helicity states. It is much more like a spin. So this is your, how can I move this stuff? So this is much more like, so the light front helicity lambda, which J is the operator, lambda is the eigenvalue, is defined as the total angular momentum minus something that looks like orbital angular momentum. So this is much more like spin than helicity. So it changes sign under time reversal at variance with standard helicity, which does not change sign. So all of this to say that please work out the details in really careful manner, because, and what I said yesterday, that okay, time reversal maybe is not the best thing to do. Maybe you should use PT just to get this, to map plus quantization into plus direction into quantization into plus direction. And you can see that it is basically what also Soper suggested with this extra rotation along the z-axis. This is kind of course, I didn't invent anything. It is kind of standard procedure. And you just you see that that light front helicity behaves like a spin because this is under parity, doesn't change sign besides the global phase, which is kind of okay as we expected. But under PT, parity and time reversal, you get okay a global phase which has to deal with parity and time reversal, but you get also minus lambda. So it behaves really like a spin under time reversal. And okay, so the natural way to look at your theory is this, we call it the tau reversal operator, or whatever it is, parity plus time reversal. If you want to put this extra JZ, you can do it. And of course, also parity is not the kind of best way to do it, because you kind of, you have the same problem as time reversal. You switch the plus with the minuses. So he proposed to use a different kind of he calls this mirror reflection operator, which is just J, the exponential with Jx. By the way, these J's are the total angular momentum operators, which are the generators of rotation in your Lorentz space. It's just a rotation. And the parity. So everything to say that and if you are prone to investigate the theoretical aspect of this, is kind of it is tightly bound to the fact that the transverse space. I mean, you can clearly separate light from quantization, or nevertheless quantize on the light front. You can identify a Galilean subgroup, and these two, what Soper calls UR and U tau, are the more or less time reversal, time parity, quote unquote, and time reversal, quote unquote, in this Galilean subgroup. So what you really want to do is not touch your light cone directions. I mean, your theory has global symmetries, but like time reversal, the problem is that it maps two different quantization procedures onto each other. So you get really just a relation between the two quantization procedures rather than a constraint on the single one. But you don't need the constraint on single one. I mean, if you want the constraint on single one, you go and look to instant form. So if you really think that some object has constraints as consequence of time reversal, you just go and look into instant form, in which instead of mapping quantization onto plus and quantization onto minus into each other, you just have constraints on the time or the spatial. Just that. So I understand that this is not a complete answer, but just it is not so straightforward to check. It's not just that you plug into the spinors and you see, okay, that's the matrix that does the trick. Also, by the way, the matrix that does the trick is the same. It is completely insensitive to how you quantize your theory. So in the end, you should find the same stuff. The problem is that the way to arrive to the same results is much more complicated in this case. So it's kind of, there is no real point. This was first item, and okay, let me share just the application so you can see better. I think so. Okay, you should see it better, I think, I hope. So first of all, I will very quickly show you the transformation between impact parameter distributions and Gpds, and then I will show you, even if not in great details, how you basically from the Atomic Tensor, so it's what you call W mu nu, you get something that looks like the let me say the product of two TMDs with various matrices in between. So you get something that looks like TMD hadron A, some gamma, TMD hadron B, some gamma. This is for Dralian processes. If you go to see this, you get, instead of TMD PDFs, you get TMD fermentation functions, but there is no point. I mean, you can do it. Dralian is a little bit more clear to follow. So this is second point. First point is how we get impact parameter distributions from Gpds and vice versa. So let me just remind you that you can define a state with definite transverse position, which incidentally is the eigenvalue of the Harper operator that is present in Soper paper. And this you got basically just a Fourier transform. You define with some normalization, which is completely irrelevant. You get the integral over the transverse momentum, pi factor to put everything into position, the Fourier transform phase, and then you get just p. So there is really nothing there. Okay, here we are not using wave packets. We are using basically plane waves, both in momentum and in position. So this normalization is, strictly speaking, infinity, but we don't care. It's like it's not really different than what you do in functional integrator method. You just require that that your n square is nothing else than n squared times the integral over pt over 2 pi squared is 1, and this ensures the proper normalization for your state. this is proportional to, let's say this is p prime plus p prime plus minus p plus delta of p prime also. So this is, I mean, this is proportional sign, not alpha. So normalization is just to ensure that you get the correct delta functions when you try to take the bra and the cat of the same state with different positions and momenta. So nothing really there. So impact parameter distributions, you saw that you define it through a completely relevant for our purposes Fourier transform phase. So this is kind of, it will always be present. Forget about it. You don't care. The light composition is always the same for Gpds, Gpds, whatever. So you get Fourier transform, and then you get your P plus, and then your RT state at 0 position, and then you get your Q bar of minus Z over 2 Bt, some gamma function, and then you get your Q of Z over 2 Bt, and then P plus RT equal to 0. Nothing extraordinarily complicated, but so you see that, okay, you have at variance with and I think it was already pointed out, at variance with TMDs, in which you have separation between both the light cone and the transverse position space. Here you have just separation along the light cone, and the two fields evaluated the same position space, which, as Deal I think showed you, is the global position Bt, this where you have protons with fixed positions. It is tightly bounded to momentum transfer, the momentum view of the process. It is not really a surprise that you will get Gpds. So what you can do now is just, okay, plug the definition for any, sorry, from this you define your impact parameter distributions, just parameterizing with in the usual way as you parameterize TMDs, Gpds, whatever. You have your basically your Lorentz structure that is given by gamma, and you just parameterize, and then you have U bar and U. You parameterize in terms of full. You have to fill the full possible combinations up to Gordon identities. So, but now you just, I gave you the definition for the state. You just plug it in, and you get something that looks like, of course, you get the n square. I do not write that Fourier transform on the light cone because it is irrelevant. You get the integral over Pt, the integral over Pt prime, then you have 2 pi to the 4th, which comes from the definition of the state. Then you have P plus Pt prime, and then you have your Q bar of minus Z over 2 Bt, gamma Q of Z over 2 Bt, then P plus P. Okay. I'm not putting Wilson line. This is completely irrelevant for our purposes because it is it behaves in the same way. Okay, thank you. I saw now that I just saw that you put something in the chat. Thank you. So you get what was I saying? Okay, the Wilson line is completely relevant because it behaves like you expect on the translations and basically under everything. So it's irrelevant. You can put it, you can forget about it using light cone gauge. And I think you can convince yourself that if you plug the same transverse position in both fields, the Wilson line runs still on the light cone because it is just a different transverse position, but you are not changing the shape. So whether you run the Wilson line between minus Z half along the light cone at 0 transverse position, or so this is transverse position, this is what is it, minus direction, or you run between minus Z half plus Bt and z half plus bt. The direction does not change, so it is still light convulsive line, so you can still choose t plus equal to 0 and forget them. Should be kind of clear, I think. So now we just basically finished. You can use the what is it? What's called? You can translate your fields. So you have q of pt. You can write it as what is it the correct way to put it? E minus I bt times the momentum of operator q of 0 e bt momentum operator pt. So please, I put just small heads just to remember to remind you that these are momentum operators, so they must act on something to get you the eigenvalue of momentum. So you plug this into your correlator. You do the same for q bar. It's just it is really standard procedure in quantum mechanics. So you get, of course, that this transformation on the left for q and on the right for q bar cancels, and you're left with something that is ebt pt at that acts on p plus pt, which gives you nothing else than p plus pt ebt pt. And now this pt is not the operator anymore, is the eigenvalue, which is the momentum of the state. On the left hand side, you get pt prime e minus ebt pt operator, which is e minus ebt pt prime p plus pt prime. So you end up with the norm squared, then the integral over pt and pt prime, it's 2 here, 2 pi to the 4th, e, then you get e to the I bt pt minus pt prime. I didn't, okay, I should get the correct whatever. So here you have p plus pt prime q bar of minus z over 2 gamma q of z over 2 p plus pt. So restoring the Fourier transformation that I along the light cone that you got previously that I didn't wrote. This is just the GPD correlator. So this is just phi of gamma that depends on x, xi, and t, right? So it's your GPD or GPDs, because you can each e whatever contains the full decomposition. And now you are left with this kind of more or less ugly integral, but you can switch to average and basically difference of momentum. So you can define capital PT as 1/2 PT prime plus PT and delta T, which is PT prime minus PT. So when you compute the Jacobian of this transformation, you get unity, so you don't have to worry about it, basically. So this box becomes the norm squared, the integral over capital PT over 2 pi squared, the integral over delta T over 2 pi squared, E minus E BT delta T, and then you have your correlator gamma, it comes from here. So nothing in phi depends on the total momentum. You saw that. That's just the way it is. It depends only on the difference. You can see that also it does not depend on, it depends on x, but not on p plus. It does not depend on the total p plus. It depends on the fraction of p plus of partons over p plus, just to get it dimensional, but it does not depend on the total momenta. So say that there is nothing that depends on capital PT, and this you use your normalization condition, and this is one. So you're left with your, this is the statement, you get that your EPD correlator is nothing else than the Fourier transform of your GPD correlate. That does not mean that your GPDs are Fourier transform of your that your EPDs, impact parameter distributions, are not the Fourier transform of your GPDs. It depends on the prefactor that you have. So for the GPD H, that works because you can work it out. If you decompose phi of gamma, you get, I go by memory, so there might be factors that are not on place, that are out of place, U. Yeah, should look like something like this. And this is, so this is H x t xi plus something that should be something like this. Sigma, so alpha plus delta alpha, probably there is a minus because I used a different convention, whatever, U times E. Oh, oopsie. Times E. Perfect. So this, you can work it out. This is independent. This does not depend on delta t. Oh, by the way, if you this, of course, I used the correct convention, but I just miss whatever. This is, you see that this is p plus, this is p plus, so everything is evaluated at xi equal to 0. And incidentally, if you have xi equal to 0, t is minus delta t squared. And there is a good reason for that. If you try to include the delta plus, and you actually want to compute the Fourier transform in delta plus also, you get something that is not, I mean, you get something that is not invariant until light from boosts, but that is kind of obvious because you are integrating over delta plus, and the delta plus is not invariant until light from boosts. So you can't have also the Fourier transform in delta plus. Instead, you can have in delta perp, because the light from boosts, so boosts along the light front, are completely do not touch the transverse moment, transverse vectors. So you can do it, and you have no problems. And this is usually referred to as I do not remember how it is called. So forgive me when. Okay, relativistic correction. I did put it because I never remember the terminology. So you get relativistic correction if you try to do the integral over delta plus, just because when you try to boost it, delta plus changes instead delta t. No, and everything is light from boosts. Good. So so this is xi equal to 0. This is xi equal to 0. So this alpha is just perp index. So you see the difference. Here you get something that does not depend on delta t, and therefore you just, and h depend only on delta t squared. So you try to compute the Fourier transform of some function that depends only on delta t squared from delta t to bt. So if you are trying to compute something that depends only on delta t squared, you get the Fourier transform of f. So let's call it field or whatever, that depends on bt squared. So this is just general, very, very general results, and you can work it out exactly the look of it. Instead, in the second term, here, you get something as the Fourier transform of delta alpha g of delta t squared, delta t into bt. And this is equal, implies, was some kind of small algebra. This is nothing like b mu. Yes, b alpha, sorry, not b mu. And then the derivative over b squared of your Fourier transform of g of delta t squared, delta t bt, right? And this is g tilde of bt squared. So For the H distribution, you just get its Fourier transform. For the E distribution, you get this combination that looks like D alpha, and then you have some prefactor that is contrasted with alpha, comes from all this stuff. And then the derivative over B squared of E, evaluated at BT squared. So they are different. I mean, you can see this is not the Fourier transform of E, it is the derivative over compared to B squared of the Fourier transform of E. So that is to say, EPDs are not directly the Fourier transforms of GPDs, but they are related up to derivatives. So I think, I mean, if you have questions on this part, please ask. But I guess it should be. It's actually there is not much. Okay. Please, whatever, please ask. Now, on the second topic, I will go very fast, I think, just because I do not have enough time to cover it in details. So please forgive me, but really there is no time to do it extremely in extreme details. So, but I refer to a specific paper, which is actually, I think, a little bit different to what you see in lectures from Barbara Pasquini and etc. Just because, okay, the traditional way is presented in both books and paper by the Amsterdam schools of Mulders and all these co-workers. But I think that, okay, since now I'm in Regensburg, I do another shameless plugin, even if I'm not one of the authors of the paper. So recently it came out a paper by Alexei Vladimirov, Ignacio Shimemi, and Valentin Moos on the title is, you can look it is one of the most recent papers. The title is Transmomentum Dependent Operator Expansions Next to Leading Power. So it's very informative title, not very catchy, but what basically it establishes is a complete and thorough proof of TMD factorization at next to leading power. So it is kind of a milestone in the field. And the starting point is, of course, a process that actually has TMDs in it. And okay, just to avoid complications with fragmentation function, you can study joint. And that's fine. And also one nice thing that it does is that it uses a technique that is known as background field techniques. So background fields is the name, or usually it is also called, or traditionally is also called.
Sorry, Simone, can I ask you a question?
Yeah, sure.
You say to avoid problems with fragmentation function. What kind of problems there should be? For example,
nothing is just it's a little bit less nice, and you have to kind of work into different mind concepts. I mean, fragmentation functions are inherently different from TMDs. TMDs are hadronic. What is this? Hadronic matrix elements. You should see my screen yet. Still, yes.
I can see the remarkable.
Okay, perfect. Fragmentation functions instead are vacuum matrix elements. So it is a little bit different, and also usually you study different different spin structure in fragmentation function. You usually see pions instead of spin 1/2 particles, or you see in 1 particles. You have different also, I mean, parameterization for the correlator. It doesn't really matter if you work at the operator level. It's just a little bit more clear and a little bit less cumbersome to work with just Drellian process in which you have 2 TMDs, and but you can do also. I mean, CDs has 1 TMD PDF, 1 TMD fragmentation function, and you have basically the opposite of Drellian, in which you have 2 fragmentation functions. Basically,
Yeah, I think it's a bit more clean with the Reliant process, because
yes,
we have
so it is
PDFs.
just out of convenience for me, but you can the paper that I cited is generalize it. You have 3 different regions that depends on the. I mean, the other difference is where your Wilson line runs, because of course you for fragmentation functions you runs in different directions. But you can do it. I mean, it's not if you are interested in details to how to relate Dualian series and just in a kind of completely general way, you just please look at the paper. It is really there's lots and lots of details. It's like 70 pages. It's more book than a paper, but it is really clear. I mean, follow it. You have all the details that you want.
Okay, thank you very much.
You're welcome. So the what I was saying is that okay, I will use background field. It is also this, you can look extensively in the literature. It is basically the idea of putting classical sources of your fields. So you put sources which you call background fields or classical fields, and you just compute the quantum correction. So when you write a Feynman diagram, usually you write something, let's say like this. Maybe you have some photons. Maybe you have another box. You have something like this, right? When you write a generic Feynman diagrams, and this you call external states. So in scattering processes is in and out states, and basically they are classical. I mean, at some point they do not have more interactions. They just are states in your theory. They're just electrons and positrons in the initial and final states. But in the middle you have kind of what is typically quantum, so you have interactions. So the full idea is of background fields is to, for a generic field phi, is to introduce a copy of it, which you call background field, plus a copy of it, which you call dynamical field. The dynamical field is the one that is allowed to have this kind of interactions. The background field instead is not allowed. But your theory is written usually as an action that depends on the field phi, the total one. So this will be split as something that is only for the background, plus something that is only for the dynamical, plus some interaction Lagrangian that depends both on the dynamical and on the background. There is really nothing there. This is also standard technique with which you manipulate functional integrals in path integral formulation of quantum field theory. So you put basically a source, and you pretend that this background source is your external state. That's it. And then, of course, what you have that the dynamical Lagrangian is what governs this kind of inner part of your process. The background is what gives you the external states, and your interactions. It is what relates. For example, at this corner, you would get something that is a dynamical field that enters. So this more marked line is dynamical. A dynamical photo that enters because it leaves, basically it is virtual, and then you get something that exits, which is which goes into the final state. So this is back. This is back. And the coupling of the coupling looks exactly like the standard coupling. There is nothing really there, but but you separate your degrees of freedom. You basically introduce two copies, and the complication when you do Drelian or CDs or double fragmentation processes is that you do not you can't introduce just one copy of your background field. You have to introduce two. It is a little bit complicated at the beginning, but it becomes extremely clear at the end. So what you do, usually, for example, in Drelian, you have a proton that moves fast in the n direction, something else that moves fast in the n bar direction, and then you have your process in between. So you have two directions that are identified from one proton and the other proton. The first assumption that you do is that, okay, a proton that moves into the n direction contains only n collinear partons. So if any of you works in the SCAT literature, in the SCAT field, you will be familiar with this. This basically just means that the partons are collinear with the n direction. For n bar, the same stuff with n bar collinear. And this is nothing else than what we do when you basically, when we quantize on the light front, we say, okay, the plus direction is the good one. And we care about that because the proton is moving in the plus direction. If it was moving in the minus direction, we would have said exactly the contrary. And here you have one that moves into the plus, one that moves into the minus direction. So you can just do that. So now let's say that our field phi is a generic QCD field. So it could be Q field or it could be a mu field. I do not care about the details. Just you do exactly the same for quarks and gluons. And if you have other theories, you do also the same stuff for whatever, if you include the electroweak corrections and stuff. So you introduce two copies of background, one that you call n collinear, one that you call n bar collinear, and one that you call dynamical. And I will not put anything for the dynamical field. So please remember that from now on, I will always separate. And I will say when, okay, I use the total field phi or the just phi, just the dynamical, that should be cool. Another thing that you can do, I mean, okay, now we introduce the two fields. The problem is how we write the Atomic Tensor, right? So the Atomic Tensor for, let's say, the Relian, this is a Fourier transform. And you have the sum over all the intermediate states. So if this symbol indicates sum over discrete the degrees of freedom and integrals over everything else. And you have proton number 1, proton number 2. Then you have your J mu dagger of 0. Then your X state. And then you have your X state, J nu of Y, proton number 1, proton number 2. So this is the Atomic Tensor for Relian. Yeah, the problem is now that you would like to use functional integration methods, just because I told you that this background is kind of intimately related with functional integration method, also because it is much simpler. The problem is that you have products of two operators that do not that are not time ordered. So what you can do is you completely ignore the problem altogether, and this is kind of I'm telling you like it is a trick, but it is well established and it's kind of okay technique. You introduce, upon the decomposition into background and dynamical, you introduce a second decomposition. So phi n plus phi n bar plus phi goes into phi n plus, which has nothing to do with good and bad components. This is different notation. This is different meaning, and I will tell you what it is in a second. And then you have phi n minus plus. Sorry, this is not really a plus. It depends on what you in what sector you introduce them. Plus phi minus. This is basically you introduce a copy of QCD fields for the conjugate of the current, and one copy for the J nu current. Because of how you interpret these plus and minuses, the new current gets the plus fields, the minus current gets the minus. So sorry, the conjugate current gets the minus field. What does it mean? So the Atomic Tensor is basically is nothing else than a blob, right, between proton proton, proton proton, and it represents the cross section. So what you do is that, okay, we introduce a copy of the background field for the amplitude and a copy for its complex conjugate. And of course, since if you describe the complex conjugate of the amplitude as an amplitude, so you do not see it as the complex conjugate of the amplitude, but you call all this left, all this right object, you call it an amplitude, and you just say that, okay, it is the product of these two. This entails that you have to use anti-time order and anti-causality to write your theory. Otherwise, you get something nonsensical. Instead of getting a cross section, you get an amplitude squared, not modulus squared. So to get really the amplitude squared, you have to ensure that what is the complex conjugate of the amplitude behaves like you expect from a complex conjugate of the amplitude. So there is anti-causality and anti-time order. What does the only constraint that you put is that, of course, on this cut, the two representations should be the same, but you have to have the same representation at infinity. And what it is basically what you ask. You plug boundary conditions that your total, let me say, total field plus at t plus infinity, it is the same as your phi minus at t infinity. And when you have interactions between plus and minuses field, it is just the real propagator because it propagates along the cut. So it connects plus and minus field. So it means that it is something that crosses the cut. And that is just the real propagator or the cutted propagator or whatever you want. Now you basically have all the ingredients, and we can write our hadronic tensor using these two decompositions. Basically, you introduce the two decompositions, and you just write it in the functional integration way. So let's say that our QCD, this is the functional integration measure, so it contains, let's put the intro, it contains the vacuum normalization, it contains, if necessary, already remove the Gribov copies of QCD fields. So it is kind of compact notation for everything you have to taken care of for writing a functional integration version of QCD. So it's kind of extremely compact. And this, you write it as, first of all, you separate between plus and minuses, and then you separate between n bar and dynamical for the plus, and the same for the minus. So instead of one integration measure, you get 6. And in QCD, of course, this phi is a collection. When you do functional integration, phi is a collection of q bar, and a mu. So you get a lot of integration measures, right? But each of them represents a specific and unique sector of your theory. So you just separate out what is already there. It becomes quite a mess, but not a mess. It becomes quite lengthy to write, but please bear with me. So now I will show you just the formulas from the paper, just because it is much faster for me. So if you plug the decomposition that I show you, and you just write explicitly that you have q bar, q, and a fields in your theory, you get the first line, which contains the n bar collinear fields in the plus and minus sector. You get your QCD Lagrangian, QCD action for the plus n bar fields. And when you go to the anti-causal sector, you get of course a minus I in the action, because it is anti-causal minus from the anti-time order. So you get S minus of n bar. You do the same stuff for n collinear, and you do the same stuff for dynamical fields. So you just get, they are basically 3 identical copies for n bar and dynamical. Then the assumption that comes in. So you get the 2 proton states in the, this is basically the ket. These first 2 pieces is the ket P1, P2 that I wrote before. This is basically the bra of P1, P2. So since the ket lives into the complex conjugate of the amplitude, you get that is built up of minus fields, and they are incidentally starred. This represents the hadronic wave function is basically a way to write the state. And then you have your complex conjugate current, which depends, of course, over your minus fields, because it is the complex conjugate current, and it depends over all your fields. So it is just the minuses, but you have dynamical and bar and then collinear. And for your current, you get only plus field, you get dynamical and bar and then fields, and then you have your ket for P1, P2 built only of plus fields, and you get everything that is missing from the interaction Lagrange from the actions of QCD is contained in this. So this contains how's it called, all the interactions that you have between dynamical and background fields. The expressions are extremely lengthy because you have just a proliferation of terms, but okay, you don't really care. You just write them. And you see that basically the interaction Lagrange is nothing else the total minus the 3 copies that you use to define these 3 measures. So now for the background field, you don't care about anything because you just, okay, everything that is dynamical for them is included into this hadron wave function. So you actually do not care. For your process, the only thing that you care is the dynamical part of the fields. And therefore, you can actually compactify your notation. This is the first 2 lines are the same. And here enters the assumption that your protons are either in the n direction or in the n bar direction. So you see that P1 here is assumed to moving along the n bar direction, so it contains only n bar fields, and P2 is assumed to move along the n direction, so it contains only n collinear fields and no dynamical fields, because by definition the proton states are the external states of your theory, so they can contain only the background fields. And then you have whatever operator in between, and then you have the same stuff for the ket for your ket state for P1, P2, and this whatever operator is the functional integral over the dynamical components of your fields. So you integrate out the components, so you basically are writing the loop structure, whatever that you can also do at 3 level. You're not supposed to do loops, but this can contains loops in the dynamical fields, and you have the product of your currents, the interaction actions, and the free part of basically the pure dynamical actions for plus and minuses. So what you actually do now, you see that plus and minus sector are completely separated in this effective operator, so you treat them independently because there is no interaction between them. And okay, you can just do some very general results. Then here there is a lot of discussion, which for us is completely relevant. Okay, so what you can do now is what is traditionally done. You can actually write what the current is. So the current is just, it was the electromagnetic current, so it was Q bar gamma mu Q, and you expand it, this Q bar gamma mu Q, you expand it using the separation of your fields into n collinear and bar collinear and dynamical. So you see that, okay, this is organized in 3 rows because there are meaning into it, but you have, for example, you can see that you have, when you take gamma mu Qn as a structure, you have Q bar and bar, then where is it the other? You have psi bar, and you have Q bar n. So this last term, this and this, if you sum them, you will find that you have Q bar n, Q bar and bar, Q psi bar, gamma mu Qn. So, and you recognize one of the pieces of the expansion, and you can do the same. You can play the same game with all the others. So what you can do now is classify this. So which one are which one appears at leading twist, so which one is the base case, and which one appears at higher orders or higher powers of your suppression. So in languages of collinear pattern distribution, you would call higher twist contributions. So the first row is the leading part, which contains one n field and one n bar field. The second row contains also dynamical fields, so it goes higher in the loop order, so because you have to kill these dynamical fields because they are not in the external state. And the last one is for maybe too complex reason to explain right now, but if you connect the same kind of patterns across the current, you get next to next leading power. So they are suppressed and they are what you could call twist 4 in the collinear center. So if you want to isolate the leading power from this, you can just you have to look at on this kind of you have to expand these fields. So let me just give you a very rough idea, and I think I will go 5 minutes longer, but please forgive me. So let's take just one of the fields. Let's say we have Q of n bar that depends on y. You can write it. I mean, you can Taylor expand this this background field. There is nothing there. What you can do is Taylor expand it into y plus. So what you can write is that this is Q n bar of y minus n plus yt plus you have y plus d minus Q n bar of y minus n plus yt plus dot dot dot. This is just the Taylor expansion of your field. Now, what you observe is that you have a minus derivative over Q n bar. So, but the minus derivative is basically, if you switch into momentum representation, this is basically represent the minus component of the momentum of Q n bar. But I told you that n bar means that it moves collinearly to n bar. So it has dominant plus component. So if it's moving along the plus direction, not along the minus direction. So if you have something that moves along the n bar direction, the counting for the momentum is that its plus momentum is of order 1. So it is the dominant component. Its transverse momentum is of order lambda, so where lambda is a suppression scale, and its minus momentum is of order lambda squared, so it is completely suppressed, because if it is moving along the plus direction, it can only have a very, very, very small momentum along the minus direction. So basically, this contribution right here is suppressed by order lambda squared. So if you want to do just a leading power, so leading order, when I say order, I mean in this suppression parameter. When you want to just compute it completely 3 levels, so leading power, leading order, you can get rid of all these order lambda square contributions. And if you have a pattern that is n collinear instead of n bar collinear, the plus and minuses in these relations are exactly interchanged, and therefore you get this kind of expression where you have the Qn that is y plus yt, Qn bar that is y minus plus yt. With this logic, you could also completely forget about yt, but not really, because of trickery arguments with the Fourier transform. So yt, you have to keep it, unfortunately. Plus everything else is depends on the derivatives of this field, so it is order lambda squared. So we don't care about it. Then, okay, here you just select the good components of these fields, because bad components are even more suppressed. What you end up, forget about this psi, for you can be just the Q, it doesn't matter right now. You end up with something that looks like q bar gamma mu q, q bar gamma mu q, but with the correct dependencies over the position plus and the position minus. So this is just the electromagnetic current, which basically you're used to, separated between n bar and n, and with just the leading power term included. So when you combine the two into your effective operator, since this is leading power, leading order, all the interactions, so the functional integral, the actions, you can get rid of them because they do not matter. This is a leading order. And you get the first two contributions that we just saw in the minus sector, and the same two contributions into the plus sector. One was evaluated at position y, the other at position 0, but the same argument for the expansion works in position. So, and now you have to basically combine this, but you have to combine this in such a way that makes sense for your final state. So you have to translate proton 1 into proton 1 and proton 2 into proton 2, because you cannot connect proton 1 to proton 2 because that would be suppressed in the powers, because you have to connect plus and minus direction. So you have to connect proton 1 to proton 1 and proton 2 to proton 2. So what you can do is just, okay, in principle you have 4 terms, like, because you have 2 times 2, you have 4, but two of these 4 terms are irrelevant because they connect proton 1 with proton 2. So for example, you can see that here, for example, this second one with the second one, you try to have psi bar n, psi n bar, which is bad. I mean, you have to saturate more or less the Dirac structure. So you would try to have psi bar n, psi and bar, which connects n and bar. So that is bad. So the only allowed combinations are the first with the second. So this one with this one, and by symmetry, this one with this one. And when you do that, you just have a product, and you can, let's look at, for example, the first two. When you take the product, you get psi n, psi bar n, gamma t nu, psi n bar n bar, gamma mu t, which is exactly this operator, this combination right here, where if you read the order of these matrices, you see that you start with this OJK bar with n, so just focus on this n, and you go to gamma nu, then you go to this O n bar, then you go to gamma, which is exactly the order that I read them. And the interpretation of this object is this ON contains, as I read it, it started with psi n, then it went to psi bar n, so it is this one. And the other instead starts from psi n bar plus, it goes into psi bar and bar minus, so it is basically the other way around in the order plus minuses. So the first row is basically the quark TMD, and the second row is basically the anti-quark TMD for the second. So here you get basically the trace that I wrote you. This is written just not as the trace, but you plug the string of the indexes. You see that is basically a trace. It is written as a trace, in which you have the anti-quark TMD for the proton, what was called proton 2, and the quark TMD for the proton 1. And then, of course, you have the reverse case in which the antiproton comes from the proton 1. So you have the TMD for the anti-quark from proton 1 and the TMD for the quark from proton 2. And this is basically your Atomic Tensor at leading power, leading order. Then you can play the game of going to next to leading power and also include loop correction. That becomes the main topic of the paper that I'm showing you. So, but 3-level Parton model, this is the result. And you can use other arguments, but I think that once you get used to this language of background fields and power counting, this is extremely linear. So I gave you just the excuse to look into this paper, at least the first like 20 pages. It gives an overview of the method. So the full logic is explained in a few pages without many formulas, just kind of general discussion. And then you get to the leading power, leading order results. And then if you're very, very interested, you can go tree order, next leading power, then next leading power, next leading order, leading power, etc. By the way, I said that, and then I will leave you. I said that you have, and you can separate between n and n bar fields, but this is kind of okay if their momentum is large, but there is a region in which their dominant component of the momentum is not so large. And if I can find the picture here. So these derivatives are basically the plus momentum and the minus momentum. So for Qn, the minus momentum is large, but at some point, and the point is exactly given by this lambda squared, its minus momentum is kind of small, even if it should be the dominant component is kind of small. The same happens for for n bar fields with plus momentum. So you basically are double counting this soft region, and the name is not random. And exactly this double counting of the soft region is what gives you the rapidity divergences that you heard about. And I think Marcus told you that you can reabsorb the rapidity divergences by basically including the square root of some factor into your TMD definition. And it is exactly that procedure is exactly reflected into the division by this region to remove the double counting. So you double count it and you subtract one of that. So you have 2 minus 1, which is 1, which counts this region exactly once, so it is correct. And the rapidity evolution is how you actually separate. I mean, is the change in how you separate these two regions with these two n bar and collinear regions. So I understand that this last part was very, very fast. And please, if you are interested in this stuff, read the first few pages of this paper. You will find it very instructive, or at least I did. If you have questions now and you don't want to go to lunch, I can answer them. Otherwise, you can go to lunch, write me an email at some point, and I will do my best to answer them by email. Sorry to take in.
Thank you, Simone. Just before closing, there was a question on the chat. Someone asked for the title.
Yeah, I will give the archive reference.
Okay.
If I can manage to copy it. So this is the archive reference. Now it's published, but you can download the published version. Okay.
So if there are no more questions, we thank Simone again for his hard work, and we reconvene this afternoon at 2 o'clock.
Okay, thank you very much.
Simone.
Goodbye.
Thank you, Simone. Bye-bye.
Bye.